Hi folks, this is Heath. Happy Friday. We're on section 15.4 today. That's a section on polar coordinates, and we've already started polar coordinates. We're wrapping up polar coordinates today. We're going to talk a little bit about mass and center of mass today, and then start triple integrals next week. So let's get started. One of the things I heard on Wednesday as feedback from the video is I went a little too fast through of the examples. And so what I'm doing is I'm starting with some examples from last time. So this is an example from last time. And we want to just try to take these examples a little bit more slowly. If you have not plotted functions in polar coordinates before, it helps if you've never done this before to make a table of values with theta as your input value and r as your output value. Okay, and we can try a couple of the common values like 0 and pi over 6 and pi over 4, pi over 3, maybe pi over 2. I'm going to have to go down here also and see what happens. Okay, so to make this table a little bit easier to follow, I'm going to go ahead and put a middle column here. So I'm going to erase this r and then make this, go ahead and calculate out what 4 cosine of 2 theta is. That's sort of an intermediate step, and then we'll get an r value. So when theta is 0, cosine of 0 is 0. No, cosine of 0 is 1. 4 times 1 is 4. And since r squared is equal to 4, r is going to be plus or minus 2. Okay? And so if we plotted that, when our angle is 0 degrees, or actually 0 radians, we get a radius of plus 2 and minus 2. And so these 2 points are on our shape. When theta is pi over 6, then we're taking the cosine of pi over 3. Cosine of pi over 3 is 1/2, and 4 times 1/2 is 2. And so the radius is plus or minus square root of 2. And so if I'm looking at an angle of 30 degrees, my radius is a little bit bigger than 1 and a little bit bigger than -1. And so we'll connect these two pieces, connect these 2 pieces. All right, let's keep going. When theta is pi over 4, 2 theta is pi over 2. Cosine of pi over 2 is 0. And so we get a 0 for this. And so when my angle is 45 degrees, my radius is 0. And so this point connects into here, and this point connects into here. And then strange things start to happen. When theta is pi over 3, 2 pi over 3 is in quadrant 2. And in quadrant 2, cosine is negative. Cosine of 2 pi over 3 is -1/2. And 4 times -1/2 is -2. And r is undefined because we can't take the square root of -2. When theta is pi over 2, we get -4, and that's undefined. In fact, we get undefined radii all the way until we start working back into quadrant 4. And if we go down to angles like -pi over 4, then we get back to 0 again. That is, at an angle of -pi over 4, the radius is 0. at negative pi over 6, the radius is 2. 4 cosine 2 theta is 2, and so this is plus or minus root 2. And so we get a point here and a point here, and we can connect those 2 points and then come back to our 2. And so right in this region, R is undefined between these angles here. Okay? And so I only have defined angles between 0 and pi over 4, and between negative pi over 4 and 0. Okay? And so when I want to set this up to integrate in the order dr d theta, my theta has to be within this range. Okay? And so I can't get the entire area by integrating all the way from 0 to 2 pi. And so what I suggested last time was just to integrate from 0 to pi over 4, which gives us this area, and then we would multiply by 4 when we were done. Except I don't think I actually remember to write down the 4 when we were done. So then the radius is the square root of this. And so it's going to be 0 up to the square root of 4 cosine 2 theta. And then since we're trying to find area, what goes in here is just an R. For area, we always use 1. But when we're integrating in polar coordinates, we have to take our function and multiply it by r. So this is a 1 times r that's going on here. Okay? All right, so we have set up this integral. We've drawn the lemniscate. We have explained why we can't integrate the entire shape because sometimes we get undefined r. And that would be an improper integral if we went all the way around. So we only go from 0 to pi over 4, and then we'll multiply by 4 when we're finished. So now let's work through this inside integral. The inside integral is r squared. Let's just work this out on a separate line here. 0 to root 4 cosine of 2 theta. R dr is r squared over 2 from 0 to the square root of 4 cosine 2 theta. The r squared and the square root cancel each other out, and we get 4 cosine of 2 theta over 2 minus 0 over 2, which is 2 cosine of 2 theta. So we've taken care of the inside integral, and so the answer is going to be 4 times the integral from 0 to pi over 4 of the answer that we got, which is 2 cosine 2 theta d theta. The integral of 2 cosine 2 theta d theta is sine of 2 theta from 0 to pi over 4. This we do by using u substitution. U is equal to 2 theta, and du is equal to 2 d theta. So this part becomes u. This part becomes du. And we could have left this in the form of sine u, but our bounds would have changed. I changed it back to sine 2 theta and left the original bounds. When theta is pi over 4, 2 theta is pi over 2. Sine of pi over 2 is 1, and so we get 4 times 1. And when theta is 0, sine of 0 is 0, so 4 minus 0, and that turns out to be 4. Okay? So the area enclosed by the lemniscate is exactly 4 units. That's not obvious, and it may be a little surprising, but that's the area. Okay? So let's try one more example, and then we'll move on to the new stuff. Find the area in the first quadrant enclosed by the cardioid, 1 plus sine theta. So again, if you're unfamiliar with what this looks like, make a table of values. When theta is 0, 1 plus 0 is 1. When theta is pi over 2, 1 plus 1 is 2. When theta is pi, 1 plus negative 1 is, or 1 plus 0 is 1, sorry. When theta is 3 pi over 2, 1 plus negative 1 is 0. I'm not plotting a lot of values here, but I'm plotting enough to get you a sense of what's going on here. When theta is equal to 0, the radius is 1. When theta is pi over 2, the radius is 2, so we go further away from the origin up here. When theta is pi, the radius is 1 again, and so the radius comes back in towards the origin. And then at 3 pi over 2, the radius is 0. And so in the downwards direction, there is no radius. And so we come into this 0 and then come back out. And we get what's sort of an upside down heart shape, and that's where the name cardioid comes from. And the question is just to find the area in the first quadrant enclosed by this shape. So that's the piece that we're looking for. And so we're only interested in the angles from 0 to pi over 2. And the radius goes from 0 out to 1 plus sine theta. The radius always starts at the origin, and then it goes out to the boundary of the figure. Again, for area, we normally just put a 1 here, but in polar coordinates, whatever we put here gets multiplied by r. And so we get dr d theta. We'll work out the inside integral first. 0 to 1 plus sine theta. R, dr, is equal to I don't want to do that. I want to just write this as r squared over 2, 0, 1 plus sine theta. And we get 1 plus sine theta squared over 2 minus 0 over 2, which is just 1 plus sine theta squared over 2. All right. All right. So what we need to do now is integrate this function from 0 to pi over 2. And this is going to be a little tricky. So we have to integrate from 0 to pi over 2. I'm going to go ahead and take the 2 out here as a 1/2 and FOIL this out. 1 plus sine theta squared is 1 plus 2 sine theta plus sine squared theta. And we can break this up into 3 integrals. So it's 1/2 times the integral from 0 to pi over 2 of 1 plus 1/2 times the integral from 0 to pi over 2 of 2 sine theta plus 1/2 times the integral from 0 to pi over 2 of sine squared theta. Okay. Well, this isn't hard. The integral of 1 is just theta, and we'll plug in pi over 2, and so that equals 1/2 times pi over 2. This one's not so bad either. In fact, I'll change colors for this step. The 2 and the 1/2 cancel. The integral of sine is negative cosine, and so we get the negative cosine of pi over 2 minus the negative cosine of 0, and that turns out to equal 1. This is the hard one. And so I wanted to take a moment and talk about this one again. This is an even power of theta, and we have to use a substitution formula to solve this. And the substitute formula is that sine squared of theta is the same thing as 1 minus the cosine of 2 theta divided by 2. And so this is plus 1/2 times the integral from 0 to pi over 2 of 1 minus the cosine of 2 theta, d theta over 2. I can pull the 2 out again and get a 1/4. So this is pi over 4 plus 1 plus 1/4, and then break this up into 2 integrals again. 0 to pi over 2 of 1 plus 1/4 times the integral from 0 to pi over 2 of cosine of 2 theta, d theta. And that should be a minus sign because this is a minus sign. That's a minus sign there. This integral, again, is easy because we're just integrating 1, and we get 1/4 times pi over 2, which is pi over 8. So now we have pi over 4 plus 1 plus pi over 8. And then this last part is a u substitution problem. If u is 2 theta, then du is 2 d theta. I need to put a 2 inside here and a 1/2 on the outside. And the integral of cosine is sine. And so we get 1/8 times sine of 2 theta, going from 0 to pi over 2. Well, the sine of pi over 2 is 1, and the sine of 0 is 0. And so this just becomes 1/8. Oh, except it's the sine of 2 pi over 2. Hold on. Sine of 2 pi over 2 is 0, because it's the sine of pi, and the sine of 0 is 0. So all of this turns out to be 0. It's a shame we did all of that work and didn't get anything for it, but that's what happens. And so the answer is pi over 4 plus 1 plus pi over 8, which is 1 plus 3 pi over 8, if I combine the two terms with a pi in it. Okay? Quite a lot of work to integrate this problem, even in polar coordinates. Okay? All right. So let's move on to the new material. When we talk about a lamina, some books call this a thin plate. It's an object that technically has a thickness, but the thickness is negligible in relation to the rest of the argument. And it's uniform. It's the same thickness throughout, but we're going to regard this object as if it was two-dimensional. A couple of things we might model as a lamina would be like a tortilla, or a pane of glass, or a thin, flat piece of plywood, where the thickness is the same throughout the object and it's not going to affect the computations very much. We can just treat that as some constant that we can deal with later. Neither of these objects are truly two-dimensional, but we can often still get useful information about these objects, even if we simplify the calculations by ignoring their thickness, okay? So we're going to use double integrals to calculate the mass of a lamina by just treating the thickness as if it was constant, okay? When we talk about the density of a lamina, is the amount of mass per unit of area. When two objects of the same size have different weight, even though they're the same size, it's because the heavy object has a greater density than the lighter object. Not all laminas have a uniform density, and so we can assign a function that matches the density at each point of the lamina. And the units for that function will be in units of mass per units of area. Mass is kilograms per meter squared, something like that. Calculating the mass of a lamina mathematically is just like calculating a volume. The operation is the same. We're going to work out a double integral. We just get different units when we're done. For volume, we're integrating the height of the object, and the height is measured in, let's say, meters, and x and y are measured in meters. So the height is measured in meters, x is measured in meters, y is measured in meters. When I multiply meters times meters times meters, I get meters cubed, and that's a unit of volume. But if I change the units of the function that I'm integrating to units of density, that's mass, like kilograms per square meter, and then multiply that by something in meters in dy, and then something in meters for dx, then I get kilograms per meter squared times meters, and I end up with kilograms, and I get mass. And so in both cases, we're just taking the double integral of the function. The difference is the units of the function that we're integrating change the units of the answer. So if we integrate height, we end up with volume. If we integrate density, we end up with mass. But the good news is we don't have to learn how to do a different kind of integration. It's just the same kind of integration. The units are changing. So let's look at an example. Let's try to find the mass of this lamina. The density is 2x, and my units are in grams per square centimeter. X and y are measured in centimeters in this graph. The parabola x squared over 2 is the bottom curve, and the top curve is the line y equals x. Okay? And so we want to set up an integral to find the mass. So we have to choose an order to integrate the function 2x. And I would rather leave this as an x squared than write it as a square root of y. And so I want to leave my function in terms of y, so I'm going to put y on the inside and x on the outside. On the outside, we put our endpoints for x. The smallest x is at 0. The largest x is at 2. Then we travel in the y direction. We enter along the function x squared over 2. We leave along the function x. Okay? So this is the setup. This is going to give us the mass of the lamina. Let's work out the inside integral first as we go from x squared over 2 up to x. 2x dy. We're integrating with respect to y, and so we just get 2xy. Plug in x squared over 2 and plug in x. Well, that's 2x times x is 2x squared. 2x times x squared over 2 is x cubed. The 2's cancel, and x times x squared is x cubed. And so now I have to integrate that function from 0 to 2. The integral of 2x squared is 2/3 x cubed. The integral of x cubed is x to the 4th over 4. Plug in 0 and plug in 2. When I plug in 2, this is 2/3 times 8, which is 16/3. When I plug in 2 here, this is 16 over 4, which is... No, 2 to the 4th is 16 is 4. Okay? That's okay. And then when I plug in 0, I get 0. And so 16/3 minus 4 is 12/3 is 4/3. And my units are in grams because that's my original units. So the mass of this thin surface here is 4/3 grams. Okay? All right. This is worked out for you on the next slide. Let's try this example here. A lamina that's bounded by the circle r equals 4 cosine of theta. Let's sketch that circle for a moment. It's not the unit circle. When theta is 0, then my radius is 4. So we go 1, 2, 3, 4 units out in the direction of 0. When theta is pi over 2, cosine of pi over 2 is 0. And so at 90 degrees, we have come back to a radius of 0. When theta is pi, the radius is negative 4. Cosine of pi is negative 1, and so that's going to be negative 4. So even though pi radians is in this direction, we would be facing this direction. We go backwards 4 units, and that completes the bottom half of the circle. And then when we get back to 3 pi over 2, the radius is 0 again. And so it's this circle that's centered at 2 units to the right of the origin. Okay? All right. The density is 3 times r. Okay? So we would like to find what the mass of this lamina is. So since the circle only lies in quadrants 4 and 1, let's integrate from the angles negative pi over 2 to positive pi over 2. This is just quadrants 1 and 4. The radius is 4 cosine of theta, so 0 to 4 cosine theta. My density is 3r, but I always have to multiply by another r when I'm integrating in polar coordinates. So we remember that extra r for polar coordinates, and that gives me 3r squared. Okay? All right. So let's work out the inside integral first. The integration from 0 to 4 cosine theta, 3r squared. The r is r cubed from 0 to 4 cosine theta, which is 64 cosine cubed theta minus 0. And so now we have to integrate from negative pi over 2 to pi over 2. I'll take the 64 outside. And there we have another cosine to a power, but this time it's an odd power of cosine. And we can do that by rewriting this as take two of the cosines and rewrite cosine squared as 1 minus sine squared. And then take the third cosine and leave it like this. And then we're going to do a u substitution. U equals 1 minus sine squared theta. Du is equal to negative 2. No. Got the wrong u. Sorry. U is just sine theta. Du is cosine theta, d theta. And so this becomes 64 times the integral of 1 minus u squared. All of this becomes just du. But my bounds change because u is sine theta. Sine of pi over 2 is 1, and sine of negative pi over 2 is negative 1. All right, the integral of 1 minus u squared is u minus u cubed over 3, and we're going to evaluate that at 1 and negative 1. When we evaluate it at 1, we get 1 minus a third, which is 2/3. When we evaluate at negative 1, we get negative 1 minus negative a third. And so that's minus a negative 2/3. And so we get 64 times 4/3, or 256. That's a 5 thirds. Okay? 256 thirds. All right. The calculus gets hard at this point. These are integration techniques that you may not have done in a while. How do you integrate an odd power of cosine? How do you integrate an even power of cosine? What are all those tricks that you might have forgotten from Calc 2? If you have questions about those, let me know what questions you have. Post them on Piazza, send them to me in email. Come by my office hours. I'm happy to help work through these things. Okay? All right. So we've talked about how to calculate the mass. The center of mass of an object is the point on which that object would balance, where the mass is completely centered around that point. And that requires 3 integrals. First of all, we need to know what the mass of the solid is. That's just a regular integral of the density function. The second thing that we'll need to do is multiply that density function times x, and then multiply that density function times y, and then we're going to integrate again. Okay? These are called the moments of the lamina. And the units are going to be mass times length. We get an extra length here. So instead of just getting a unit of mass, we get something called like a kilogram meter here. These moments are named kind of odd. This is the moment my, and this is the moment mx. To get my, we are multiplying by x. When we get mx, we get multiplied by y. And at first that seems a little strange, but if we have some sort of object and we're trying to find the center of mass, then we're trying to find out how much mass is distributed on the right half of the y-axis and how much is distributed on the left half of the y-axis. But the further away that mass is distributed, the more torque it exerts, the more leverage it exerts on the y-axis. And so that's based on the distance from the y-axis, but the distance away from the y-axis is actually the value of x. So x is the distance from the y-axis, which measures, I mean, there's a reason why they have named it this way. But the naming is a little confusing if you've never seen it before. We have to multiply by x to get a moment. We have to multiply by y to get a moment. Okay? And then we divide those moments. And again, this on the left-hand side, we have my. On the right-hand side, we have mx. Those moments, those names are a little bit unusual. Divided by the mass. Okay, so if we wanted to just abbreviate this, this is just my over m, comma mx over m. And this gives us the coordinates, the x-coordinate and the y-coordinate where the shape would balance. This is the center of mass. Okay? So let's look at this example. We have already calculated the mass of this lamina. We found that it was 4/3 grams from a previous example. Let's try to find the center of mass for this lamina. Okay? So to find the center of mass, we're going to have to do two double integrals. So let's do my. That's going to be the integral from 0 to 2, x squared over 2 up to x. The density function is x is 2x. And for my, we multiply by x again. And so that's going to be the integral that gives us my. Okay? So the integral of my is, let's see, do the inside integral first. That's going to be 2x squared y from x squared over 2 up to x. That's 2x cubed minus x to the 4th. And then we'll integrate that from 0 to 2. This is going to be x to the 4th over 2 minus x to the 5th over 5. And so when I plug in 2, I get 16 over 2, which is 8. When I plug in 2, I get 32 over 5. And when I plug in 0, I get 0. 8 minus 32 over 5 is 8 over 5. Okay? So that's one of the integrals. The other integral we'll have to calculate is mx. And that's going to be the integral from 0 to 2, the integral from x squared over 2 up to x of 2x. This is my density, but this time I multiply my density times y, dy dx. The inside integral becomes x times y squared. The 2 and the y integrate to become y squared, going from x squared over 2 up to x. So then this is going to be x times x squared is x cubed. X times x to the 4th over 4 is going to be x to the 5th over 4. All right, we have to integrate that from 0 to 2. The integral of x cubed is x to the 4th over 4. The integral of x to the 5th over 4 is x to the 6th over 24 from 0 to 2. When I plug in 2, 16 over 4 is 4. When I plug in 2 here, 64 over 24 reduces to 8/3. And 4 minus 8/3 is 4/3. So now we have the two moments. The masses, the center of mass, is to take these moments, which are measured in kilograms meters, or in this case actually gram centimeters, and divide it by grams. So the first coordinate will be 8/5 divided by 4/3, and the y coordinate will be 4/3 divided by 4/3. The 4/3 in the numerator comes from here, and the 4/3 in the denominator comes from up here, the original mass. 8/5 divided by 4/3 is 6/5, and 4/3 divided by 4/3 is 1. 6/5 is a little bit to the right of 1, and 1 is right there smack dab in the center. And so it looks like the balance point is going to be right about there. Okay? All right. Let's move on. One more problem. Let D be the region in the first quadrant enclosed by x squared plus y squared equals 4. So that's just the circle of radius 2. And the x-axis and the y-axis, just the first quadrant. So this is the region we want, right up here. We have a lamina that occupies this region and has this density function, x squared plus y squared. And we want to find the mass of the lamina. Well, the mass of the lamina is probably going to be easier to calculate in polar coordinates because this is a circle and this is the same thing as r squared. So if we set this up in polar coordinates, the angle just goes from 0 to pi over 2. We're in quadrant 1. The radius goes from 0 to 2. The center of the circle out to the edge of the circle. And the density function is r squared, but we multiply everything by r when we're in polar coordinates. All right. So then let's solve this. The inside integral, r cubed dr, is r to the 4th over 4 from 0 to 2. That's 4 minus 0. It just turns out to be 4. Then we integrate from 0 to pi over 2, 4 d theta. Well, that's 4 theta from 0 to pi over 2. And 4 times pi over 2 is 2 pi. And so this is the mass. To find the center of mass for this lamina, we're going to have to integrate this again to find the two moments. Okay? Now this is a little tricky because to find my, we have to multiply by x, multiply the density by x. But in polar, x is the same thing as r cosine theta. Okay? So to find my, we're going to integrate still from 0 to pi over 2 and still from 0 to 2. The density, which is r, the density, which is r squared, times r cosine theta. So now we have r cubed cosine theta. And since we're in polar, we multiply that by r, and we end up with r to the 4th cosine theta. This is my density times r cosine theta, which is my x, and then times an extra r because we're in polar coordinates. That's what the r to the 4th cosine theta becomes. All right. The inside integral becomes 0 to 2 r to the fourth cosine theta. And that's r to the fifth over 5 cosine theta. Evaluate at 0 and 2, or 32/5 cosine theta. And so now we have to integrate that from 0 to pi over 2. I'm going to take the 32/5 on the outside, cosine theta. The integral of cosine is sine. So 32/5 times sine theta, evaluate at pi over 2 and 0, is sine of pi over 2 is 1, sine of 0 is 0, and so we get 32 over 5. Okay? All right. So then we have to do the same thing for mx, and I don't have a whole lot of space left here. Mx is going to be the integral from 0 to pi over 2, from 0 to 2. This time we're going to have r to the fourth sine theta, d theta. And the first part of the integral is going to work out the same. Since I am short on space, I hope you will forgive me for skipping over the first step and saying this is 0 to pi over 2 of 32 over 5 times sine theta d theta. That is, the cosine didn't change here until we did the second integral. And the integral of sine is negative cosine. And so we get 32/5, that's a 2, times negative cosine from pi over 2 to 0. Cosine of pi over 2 is 0. Cosine of 0 is 1. And so we get 0 minus a negative 1. And this also equals 32/5. These both turn out to be the same. And so the center of mass is 32/5 divided by the original mass, which was 2 pi, comma 32/5 times 2 pi again, or 16 over 5 pi, 16 over 5 pi. All right. Y'all have a fantastic weekend. I'll see y'all around. Take care.